So, sorry that I'm not in class today, but we are going to get the math done without me there. So, we're going to talk today, we're on page 9 for those of you who need a page number. We're going to talk about sets and set notation and particularly set theory today. So, a set in math can be defined as a collection of distinct objects. The numbers on the faces of a die are a set. That would be 1, 2, 3, 4, 5, 6 on a standard six-sided die. They're usually denoted by capital letters or by a description inside curly brackets. So that's going to be looking like one of those down there. An object in a set is referred to as an element. So 5 is an element of the set of the numbers on a die. There are 3 ways of defining the contents of a set. Number 1, all the elements. So that's A equals 1, 2, 3, 4, 5, 6. A description of the set in words would be A is equal to the natural numbers less than 7. Remember, natural numbers are counting numbers, so we don't start those with 0, we start those with 1. So that's words. Or using a set builder notation to describe the set, which is the most probably unfamiliar one. X such that X is less than 7, and X is an element of the naturals. Curly brackets together is read as the set of. The line, which we are going to see right here, indicates such that, oh, whoopsies, wrong one, that wasn't a highlighter, such that, and E is read as is a member of, or an element of is usually how we read that. The number of elements in a set is written as NA. In the above example, the number of elements in the set is equal to 6. The number 2 belongs to the set A, but 8 does not. To express this, we can write 2 is an element of A, 8 is not an element of A. Anytime in math, when you have something and you put a line through it, that means is not. So the order of listing the elements in a set doesn't really matter. It's kind of like addition and multiplication. You can write those things either way. So if we're looking at the following sets, so the set P, and I'm just going to kind of leave those notations on the board. So when I'm reading it, when I see these curly brackets, I'm going to say P is the set of whole numbers less than or equal to 3. Q is the set of even whole numbers less than 10. So we're going to list the elements of each set inside some curly brackets. So P is whole numbers less than or equal to 3. So in this, we are going to consider 0 because it is a whole number. Whole numbers include the natural numbers. We're going to have 1, 2, and 3. For Q, even whole numbers less than 10 is going to include, wrong spot, is going to include 0, 2, 4, 6, and 8, not equal to 10. It was just less than 10. So in the number of elements in P is going to be 4. The number of elements in Q is going to be 5. That means 1, 2, 3, 4, 5. 1, 2, 3, 4. So if we want to write set P using builder notation, so set P was this whole numbers one, we are going to say in curly brackets, X such that X is less than or equal to 3, and X is an element of the wholes. So when we're talking about whole numbers, that means all of the positive numbers greater than 0, including 0. Natural numbers does not include 0. The only difference between whole and natural numbers is that whole numbers does include 0. So if we were looking at this next question here, which of the following is set builder notation and describes Q? So remember, Q was our whole numbers that are less than 10. So when we're looking at this one, sorry, even whole numbers. It must be even. That's our kind of ticket item there. So Q is the set of X such that X is less than 10 and X is an element of the wholes. So that has our wholes part, but it doesn't include our only whole numbers. So that one can't work. If we look at B, we have even, E for even such that the even numbers sorry, I don't know why they're using E all of a sudden, but E is actually indicating the numbers. What incarnation is that one here? Okay, here we go. So what it's doing is it's using X and it's using E. So X is the variable that we're still dealing with. So the numbers that we're looking at are all the X's. E is the answer you get when you're talking about these numbers. So what this is saying is that we have the equation, not E for equals. I made that up and I was wrong. The equation is going to indicate is going to be 2x. And this is saying for all values of x from 0 to 10, but not including 10. Now, the problem that we run into there is like this works for 2 times 0 is equal to 0. 2 times 1 is equal to 2. 2 times 2 is equal to 4, etc., etc. But then all of a sudden, you get to 2 times 6, and that equals 12. So for this one, the equation definitely can equal this. This part works because this is going to give us only our even numbers. But the problem we run into here is that we got to have a smaller number here. So now, if we just skip down to D, when we're looking at this one, remember that this is less than 10, not less than or equal to 10. So if we keep this 5 here with our same beginning equation, then we are going to end up with having a number that is equal to 10 when we put 2 times 5 into this equation. So that can't be it. So our only answer that we have left is C, and this is going to give us the answer. So from 0 to 4, this will give us 0, 2, 4, 6, and 8 in our set. All right. So set theory is not super tricky, but it does use a lot of very kind of weird language. So some of the terms we're going to use here. So Betty's defining sets using non-negative single-digit numbers. From the list of non-negative single-digit numbers, she defined the following sets. So single-digit meaning up to 10, non-negative meaning 0 to 9. So this first set that's even numbers is going to be 0, 2, 4, 6, and 8. The second set here is going to be L is equal to, because we're doing less than 7, 0, 1, 2, 3, 4, 5, 6, 7. And then this last one here is going to be odd numbers less than 7. So we're no longer having 0. We just have 1, 3, and 5. Note that our 7 is not included in that. So list the elements, and we're going to use these to understand some of the terms in set theory. So universal set is one of our first terms here. So within the context of any problem in set theory, there's generally some largest set that we have in mind. We refer to this as the universal set. It's the set that contains all of the elements under consideration and relevant to the problem. So the universal set here would be U is equal to non-negative single digit number.